Okay, so in my graduate math studies, we had an interesting problem for homework in our methods of applied math. And that was to find a two-term expansion for arcsin of x about 1. Now, people know how to do this for 0, but for 1 it's a little difficult, and I'll show you why in just a second. So you can get a one-term expansion super easy, and it's just pi over 2. If we try to do Taylor series, we get something looking like this. We get f of 1 plus f prime of 1. And then if you're doing about x equals 1, you need to do x minus 1. Okay, that's fine. Let's start plugging in. Well, if we take the first derivative of f, if you take the derivative of arcsin of x, you get f prime of x equals 1 over the square root of 1 minus x squared, and there's a singularity at 1 and negative 1. So we can't exactly just plug in 1. So Taylor series doesn't work. So you need to come up with something else. Now you're instructed to use the Frobenius method to do this. Now Frobenius method is used for solving ODEs, specifically second order non-constant coefficient ODEs that have specific singularities, and we'll write that out right now. So Frobenius will tell us that if our diffeq looks like y double prime plus p1 of x, y prime plus p0 of x, y, and that it's homogeneous, and then there's a special form that we can use, and we will be finding some coefficients for a series solution to this. So we're going to say that y is equal to the sum of, we'll do k as our index, k equals 0 to infinity, and we'll say ak and x minus x naught, and x naught is going to be 1 in this case, so we'll sub that in and just say 1, and that's to the k power. Okay, cool. So that's going to be our solution for a normal Taylor expansion. Frobenius says we're going to be multiplying this by an extra power of alpha. So alpha is just going to be a constant we're solving for. Okay, so you're probably wondering what this has anything to do with this problem. Well, we can find a solution to this equation in an expanded form that's not quite a Taylor form. And that's exactly what's going to happen here. Now we have to somehow get a diffeq that will give us arcsin as the solution. And I was racking my brain thinking how to do this. And well, the easiest way to do this is just to set p0 of x equal to 0. So I'll write that out. So this thing is going to be 0, and you'll see why in just a second. And then I just took these two derivatives. Okay, so we have the y double prime is going to be x over the square root of 1 minus x squared all cubed. Alright, so now what we're going to do is we're going to multiply, we're going to have a coefficient right here and a coefficient right here, and those are going to be the inverses of these derivatives. So I'll write that out. So we'll take the inverse of this, and that will be square root of 1 minus x squared cubed over x, y double prime, this, and add to that, we have to multiply that by the reciprocal, so square root of 1 minus x squared, and that is multiplied by y prime, and that is equal to 0. And instead of adding, we're going to want to subtract these things because we know that this quantity right here for y equals arcsin is 1, and this is also 1, 1 minus 1 is 0. You can check this in symbolic software or do it by hand. It's pretty straightforward. So I came up with this, and we can get it into a Frobenius-looking type of equation. Now there are some restrictions on P1 and P0. So P1 needs to look like this. So P1 needs to equal some b of x, and we're going to multiply that by, or divide it rather, by x minus 1. So x naught is 1 here. So it needs to look like it has, at most, a singularity of only order 1. Alright. Luckily our p naught is 0, so we don't really have to worry about that. But we need to make sure p1 of x is in this specific form. Now, is it? Let's check. Okay, let's multiply through here, and we'll get that y double prime plus x divided by 1 plus x and x minus 1, I've just done some simplifying here, is equal to 0. And we're excluding the singularity at about 1, so this little piece right here is going to be our order 1 singularity. You can see that. Okay, so this means that b of x in this case is going to be equal to x over 1 plus x. Okay, and now we know that we have this thing called an indicial equation, and we'll denote that as p of alpha, because we need to solve for what alpha is. P of alpha is going to be, and this is just a theory thing that people know already, right? So it will equal alpha squared plus b naught minus 1 alpha plus c naught. We want to set this equal to 0 to find the roots so we can solve for alpha. Now c is entirely 0, because c, we'll just call that p naught for now, this is 0. Right, and b naught, well, we need to Taylor expand this, and we can find a Taylor expansion about 1. And if we go ahead and do that, we get something that looks like this. So 1/2 plus 1/4 x minus 1. We don't really need that many terms. In fact, I think we only need 2 terms or 1 term. I'm not quite sure. You'll see in a second. Okay, so, and that goes on. And this is our b0 term. So if we plug that in, and we simplify a little bit, we get that alpha equals 0, or alpha 1 equals 0, alpha 2 equals 1/2. Okay, so we know what our alpha is going to be for this. We have 2 different solutions, and we're going to add them together. As in any second order ODE, we can just add the 2 linearly independent solutions together, bada bing, bada boom, you're done. And since we have 2 different solutions, and we only need 2 term expansion, we can just take the first term from each expansion, which is really nice. So in Frobenius theory, very simply, you can go through this recurrence relation and you're basically done. However, when we only need 1 term, this makes it very, very straightforward. We only need the a0 term from both of the equations. So we can say that y is equal, so we can say y1 of x, we'll do the 2 linearly independent solutions separately just to make it clear, is simply going to equal the a0 term. And we'll just denote this as c1 so we don't get confused. And y2 of x is going to be, well, we have, we'll say k equals 0 and a0, okay, so we have a0, this is a different a0, so we're going to denote them differently in just a moment, x minus 1 to the alpha, and alpha, in this case, this is for alpha equals 0, and this is for alpha equals 1/2. So you'll see, I just plugged in alpha equals 0 into here, k equals 0, and then alpha equals 1/2, and k equals 0 for the bottom one. And we'll say this is the same thing as c2 x minus 1 to the alpha. Okay, so now we have 2 terms. What do we do next? Well, let's erase some stuff here. Yeah, let's erase some of this. We don't really need this anymore. We'll get some room. Okay, so now we have our solution that looks like y of x is equal to c1 plus c2 x minus 1 to the 1/2. And this is, again, 1/2. Okay, so we need some initial conditions. We need 2 specifically for this problem. Since we have a second order ODE, well, we know what our y is going to be. We know that y of x needs to be sine x, so we can start plugging things in for that. So let's impose initial conditions that y of 0 equals arcsin of 0, and that's just equal to 0. Everyone knows that. It's kind of a straightforward thing to show. You can just look at a graph. And then y of 1 is another thing we can do. This is a boundary value problem. y1 is going to be arcsin of 1, and that's going to be pi over 2. You can check this, but sine of pi over 2 is 1. We know that. Okay, so let's start plugging in these values and see what we get. So y of x, let's start with y of 0. Y of 0 equals 0, and that will yield us, actually, we probably want to do y of 1 first. My bad. Y of 1 is equal to c1, and then the 1 here will cancel, so we'll get that C2 term vanishes, so we get C1, this is equal to pi over 2, so we can just impose that C1 is pi over 2. Now if we do the same thing for 0, we get that arcsine of 0 is 0, so this is equal to 0, and we have that C1 is pi over 2. Now this is where the fun starts, and we start working with the complex plane. One thing I noticed in graphing this, when I did not know what C1 and C2 were, was that this function was only valid for greater than 1, because obviously we have a problem where x is less than 1, we're going to have square root of an imaginary number. So that leads us to believe that C2 is probably going to be some multiple of I. And let's check ourselves to see if we're right about this. So this is going to be pi over 2 plus C2, and we're going to plug in 0 there. So we get negative 1 to the 1 half. Okay, so negative 1 to the 1 half is going to be just I. So you can do some simplification and say that negative pi over 2 is equal to C2 times I. And if we divide by I, we get negative pi over 2 equals C2. And if we want to get I in the numerator, this is just the same thing as multiplying by negative 1. So we get that C2 is equal to pi over 2 times I. And that is our two-term expansion for this particular problem. Now, if we want to do more solutions, we will just expand our Frobenius series for a higher k. Right? So we just make sure k goes from 0 to maybe like 3 or 4 or something. But it turns out this solution is really good. So let's just write out what we have. So y of x is equal to pi over 2, and we're going to add to that pi over 2 times I, and multiply x minus 1 to the 1 half. Okay, so that is our two-term expansion for arcsine about 1. And the reason this is so interesting is because it's on the very tail of this functions domain. So let's graph arcsine. So arcsine plus f, and this is x. It looks something like this. And this is 1, negative 1. Now if we go ahead and plot this on it, I encourage you to do this in Desmos or another graphing software. It actually looks very similar. It kind of overlaps and then just diverges away once you get further away from 1. But it's a very good approximation for x close to 1. And I'm very happy with how this turned out, and thank you for watching.